All right, let's talk through these. I put this box over here because maybe that'll help slow me down maybe a little bit, in addition to hopefully explaining this a little bit more. So I put 10-5 and 10-6 both together, as you can see up here. That is because they're both solving trig equations. So let's just solve trig equations all in the same thing. The first one I have is 2 sine x minus 1 equals 0. Just like everything else, so let me see if this is actually going to pull off here. Just like everything else, my goal is to get the x by itself. So when I get this x by itself, I have to isolate this. We are going to find the solution over 0 to 2 pi as well as every solution possible. All right, so that's our goal here. So if I want to simplify this, then I'm going to move this down here. And I want to get the sign by itself. So I add 1 to both sides, then divide by 2. So the same thing that's asking, you are asking yourself here, what angle measurement, just like we did with our inverse, what angle measurement is going to give me 1/2? All right. This is over the full interval from 0 to 2 pi. That's what makes it different than just our arc sine, right? So here I'm solving for this value. That is different than using that inverse trig. If I'm starting off with inverse trig, then I'm restricted. If I'm not, if I just want to know all of the angle measures that are going to make this work, because I'm talking about regular sine here, then I can go from the 0 to 2 pi, and we can pull this off. Okay, so when is sine positive? That's up above, right? Because that's your y values. It's happening here in quadrant 1 and happening here in quadrant 2. And that's how I get pi over 6 and 5 pi over 6, because it's both of these values. All right. Then the question also says, what is it for all solutions? So if I'm looking here for all solutions, then I want to say, okay, for my sine function, I know this thing is going to rock the socks off of it forever and ever. So I'm hitting it at these values every single time. So I have the pi over 6 still. And then every time I go all the way back around that unit circle, I hit this value again. Then another round, then another round, then another round. Every time I go around that unit circle, I'm adding 2 pi to that. And it can be integers, right? That's what integer is. That's a symbol for integer. So 2 pi k, where k belongs to the integers. If you're going to introduce a variable, you have to define it. Here, if I have 5 pi over 6, I'm running that same gambit, swinging it around, around, and around until I hit there where k belongs to the integers, right? And if you have a variable, you have to define it. So that's all that means. If you are restricting your answers, then you just have that restriction. If I'm saying everything possible, then I can be going on this periodic function forever, and I have to account for all of those that way. All right, so the all solution is whenever you introduce this 2 pi into it, most likely, and then otherwise it's that. Now if I had a value down here, then I could just restrict pi into it and that'd be different, but we'll cross that bridge when we get there. Okay, so for this one, I'm going to cut this, see if I can paste it on the next page. We'll see. I'm just trying new things here. Here, if I have sine, I should have left this on here. If I have sine, tangent, and sine, now here's my tip off right here. Up above on this problem, I could add or subtract and get my variable by itself. Here I've got variable with sine, variable with tangent, some more sine over here. What the heck's going on, people? So if you have that, then you need to collect all of those variables to one side, just like we did whenever we had all those x's and you had to factor it out. The same thing is going down right now. So I'm going to collect all of my thetas over here to the left. This is like saying, this is like saying xy. and this is my x. Oops, I did the wrong variable. So this is like saying xy and this is my x. So let me do like this. Then I'll take it off. If this is xy and this is x, are those like terms? No, they're not like terms, right? So you can't, whether it's trig or whether you have this variables, it has to be exactly the same in order to be those like terms, and you do not have like terms there, which means that you now have these terms. You have sine theta, and you're subtracting out that sine from it. Now you have a sign in common with both of these, and you can factor that out. Zero factor property, right? We're still using algebra skills. Just because this is trig, you're going to use algebra skills forever. You set each one of these equal to 0, and then you ask yourself, all right, so, and this is over between 0 to 360. Then you ask yourself, okay, so where is my sine value 0? Well, sine is 0 at 0 and 180. Oh, where is tangent? Because minus 1, add 1 to both sides. Tangent is 1 if I have positive over positive or negative over negative. Don't forget this one. That's a common one to forget. All right, guys, you got this. So positive divided by a positive, exact same thing, gives me a 1 because sine over cosine, right? Negative divided by a negative, exact same thing, still going to give me that 1. All right. Hey, what are we using right here? Unit circle, baby. That thing doesn't go away, does it? Ah, there's a reason why I said you guys got to, adult on this. You got to man up and get this memorized and figure it out. You have to know your unit circle. Get that thing squared away and you'll be good to go. Okay, let's do some more. Yeah, let me see if I can bring that back. I don't know if that's helping you or not. Paste. Yeah, I don't know. Now it's just whatever. So if I have this, the same kind of thing is happening. What do you see? As soon as you have something that's squared, what do you get super excited that we get to do? Yeah, we do, baby! Let's do some factoring. How exciting is that? That should totally make your full entire day. So if I'm looking at this, this is squared, a regular term and a whole number. Now we get the amazing opportunity here to factor. So do that. Do your factoring. Tangent times tangent. Minus in the back, so I know my signs are different. I need this to be positive, so I have a positive 2 and a negative 1. Let me scoot this down again. Then you set each one of those equal to 0. Okay, you set each one of those equal to 0, and then look at what's happening right here. I have x is equal to negative 2, so x is approximately here, this negative 1.107. That is outside of my 0 to 2 pi situation that I'm going for here with this, with these values. Here, tangent of x is equal to 1, so I'm still good to go because it's just like exactly what we saw last time of pi over 4 and 5 pi over 4 because I'm going between 0 and 2 pi here. All right. Okay, and this is outside, right? It's negative. I just said it was outside, but we didn't talk about exactly why. See how this is negative? I'm saying this x value, the input value here, has to be between 0 and 2 pi. This is negative. That's what makes it outside. Okay. I just realized I didn't talk about that much. It was obvious, I thought, but it's always good to talk about it a little bit just to make sure we're cool. Okay, let's roll this thing down. Oh, you get the factor again. Man, that should make you guys happy. You're welcome, right? You are so welcome. So do it. Do your factoring. Set each one of those equal to 0. And see what happens. I'm just going to throw that down all together. When I set this equal to 0, can sine ever have an output of negative 3 there? No, sir. Can it have an output of positive 2? No, ma'am. right? My sine rocks the socks between -1 and 1. These are just regular plain old sine functions. I don't have any other transformations going on. Now, if this would have an amplitude or something, that would make that impact, but it doesn't. It's just saying this is some value, this is some value. There is no possible way, there is absolutely no angle measurement that's going to give me that output. And that's why it's a no solution. All right? Okay. Let me see if I can grab this. Oh, shoot, dang. Paste that. Okie dokie. Oops, too far. Okie doke. Now, that was 10.5. And 10.6, we're looking specifically at double angles. All right, so that's the deal with 10.6. So 10.5, you're just solving what's your angle as you go through. And here, I'm looking specifically at these double angles. That's what makes 10.6 different. All right, so we're going to do a couple examples with that. So here's example 1. Good. Now, here's the kicker. I wanted to see this toolbox is what I really wanted to see. See, this isn't working. Okay. But up here, if I have this double angle, all right, I want to look at what do we know. So what do we know right now that's going to be helpful? So I have 3 options here for this double angle cosine. With those 3 options of my double angle cosine, this bottom one has a sine involved. Well, that's not helpful because I got a cosine over here. The second one has both cosine and sine. Again, not helpful because all we have is this cosine. So my best choice for this double angle cosine is to use the one where I have 2 cosine squared x minus 1, because if I replace that double angle there, now I can bring my cosines over and I have something super awesome that we get to factor. Right? So think about that. What's in your toolbox? What do we know? How can I use my trig identities in order to pull this off and make it easier to work with? So think about what's in your toolbox and then you can go with it. Okay, then factor. Once we get that factored here, I'll just take it on down. Once we get this factored, then I set each one of those equal to 0. And you get cosine by itself is -1/2. Add that 1, you get cosine is equal to 1. Then you go to your unit circle. Where is cosine -1/2? Well, to the left, and I'm going from 0 to 2 pi. So here to the left, I get at -1/2 at 2 pi over 3. -1/2 here at 4 pi over 3. When is cosine equal to +1? The only place it is, right here at 0. So I have those 3 values there because I'm restricting that domain. Pardon me, I'm restricting those values over 0 to 2 pi. Good. Okay, let's look at this next example. Oops, it's not moving for me. Ooh, check this out. Okay, so here I have sine cosine. I don't have anything over here on the right. So before, when we had the sine and the tangent on that last one, I had a sine over on the right and I was able to put it together and factor it out. Well, I don't have anything that I can put together and factor out here, right? So let's think toolbox wise. Scoot it down here to my toolbox. Doggone. So in my toolbox, we know double angle sine is sine times cosine. This is a 2 here, and I have a 4 in my problem. So I could do just 2 times 2, right? I could break that up, and then I get 2 sine cosine. Let me lose this. I feel like it's kind of more in the way, I guess, than anything. So here I've got 2 sine cosine. Just work with me up here. And so I can fix this 2 sine into sine 2x. I want to, same thing, I still want to isolate here. So because I'm going to isolate, then I divide both sides by 2, and I have this sine 2x. Right here, let me scoot this down so it maybe not be so daunting. So I have this sine 2x here. Now this is 2x. This is a double angle. All right. Typically on sine, I go from 0 to 2 pi. Well, whenever I have a double angle and I multiply everything through by a 2, I now go from 0 to 4 pi for my double angle. So when I'm looking at some values here in this 2x value, I want to say, where is my double angle sine? 4 pi, which is 2 swings around the circle. So sine at square root of 3 over 2 is pi over 3 and 2 pi over 3, right? So I have pi over 3 and 2 pi over 3. But then I also have the second swing where I add 2 pi to the pi over 3. I have the second swing around because I'm going to 4 pi. So I have 2 pi over 3 plus that 2 pi. All right. So because this is a double angle, I have to go from 0 to 4 pi so that I can make sure that I cover every single value possible. Now, when you add 2 pi to this, you just get that common denominator is all I'm doing here. So pi plus 6 pi is 7 pi. 2 pi plus 6 pi is 8 pi over 3. And that's what you get for 2x. 2x is in the blue here. So focus on that blue for a minute. Now, my question is, what values of x do I need, right? So if I'm just looking at my values of x, if you divide both of these by a 2, then same thing of dividing by 2 is multiplying by 1/2. Multiply that by 1/2, you get pi over 6. Multiply that by 1/2, the 2's cancel, you get pi over 3. Multiply that by 1/2 and you get 7 pi over 6. Multiply this one by 1/2, the 2 goes into 8 4 times, and I get 4 pi over 3. These 4 values are my value of x between 0 and 2 pi because I worked with that double angle. You see how that just went down? Okay, I can't have just this double angle. So because of this double angle, you have to put this extra step going all the way to 4 pi. Figure those out. Divide by 2. And then that puts just your values of x in front of you where you need it. Pay attention to that. If you get it down here and you're solving for double angle, you have to count for the double angle right there from the 0 to 4 pi. All right? Let's try another one. Oh, yeah. So here is, let's paste. Put this little feller in here. Pardon me. Not only can you solve these, but let's practice, because we need to practice more and more and more how to verify this identity. Oh, we're not verifying the identity. We're solving between 0 and 2 pi. Oh, but we have sine and cosine. Oh, okay. Okay, let's do this. So I am solving between 0 and 2 pi, but I do have sine and cosine here. But this one's a double angle, and this is cosine. Okay. Good. See, without looking at my other thing, then we get this set up. Now check out what just happened. Here, for sine 2x, this is only cosine. Now notice this is not a double angle. This is squared, right? So then you start thinking in your toolbox, what would be most beneficial to me? Try to break this to Pythagorean identity to put it in terms of sine. Try to work this over. Our best course of action, anytime you have a double angle, that's the one you focus on and break it down. It's much harder to solve for a double angle, so if you can break it down into just plain angles here, if you have that choice, then do it. So here we can break sine 2x down, and then now I have a cosine on the left and a cosine on the right, so when we put these two together, I can now take out the greatest common factor of cosine, right? So do that. Then whenever you factor out your cosine here, and you can factor out a 2 because there's a 2 in common, just make it easier for yourself. Then I say cosine is equal to that. Now sine minus cosine equals 0. So hang on to this for a second. I wish I could just cut, well, maybe I can just cover that up here. Let's try that out. Cover that up for a second. I don't want to mess with that. For this one, it's nice and easy, right? It's right out of the unit circle. Where is cosine 0? Oh, no problem. Right there. I have cosine 0. But over here, people ask about this one all the time, which is why I wanted to do this extra example here. So when I have sine, cosine, I want to say, where is sine equal to cosine? So what value of x can I put in where my sine is equal to my cosine? Pi over 4. Not only can I do pi over 4 where they're both positive, you can do 5 pi's over 4 where they're both negative. So this is a common one people ask me about in the homework all the time. It's one you've got in your homework, so heads up on that. This is how you work that problem out, because when you factor out that cosine over here and you're left with sine minus cosine, you can see how that plays. All right? Okay, good job, guys. Go solve some trig